Hi, good evening. Am I audible to everyone? And is the screen visible to you? Please let me know.
Yes, sir.
Okay. Hi, so welcome to the fourth live session of the points of topology. First, let me introduce myself. My name is Shavik, and um, right now, it's a scholar, Dr. Ramesh Pashaning, my class. Okay. So, okay. So before starting anything new, so first let me know. Do you have any questions or any doubts related to search class or related to any other problem solution? If you have any question or any doubt, please let me know. Don't hesitate to ask. If you have any doubt, please ask. Don't hesitate, please ask if you have any doubt or any question.
Sir, I have some doubt from lecture notes.
Sorry, can you please repeat? I didn't hear you.
Sir, from lecture
Yes,
notes,
yes,
the compactification chapter, uh, when we define the compactification x star to be disjoint union of x and infinite, the singleton infinite. So the topology defined on x star is, I did not get the topology and
okay, okay. So the x star bisect this x disjoint of some point which does not belongs to x, and the topology becomes the topology. I mean, the topology on x star is the of the following form. Uh, um, all those open set U such that U open in X union of X star minus C such that C is the compact subspace of X. These are the open set which we are already declaring that U, if U is open in X, then U is open in tau X star, and union X star minus C is a compact subset of X, and I mean X star minus C also open set. That's what we are declaring. Okay. Now only you need to check that whether this tau is actually topology or not. I mean, this satisfies those topological properties or not. This is what you need to check. So
uh,
yes,
sir, x star minus c is a closed
no, no, no. The thing
c.
is that yes, I understand that. The thing is that X is a given space and X star is a bigger space. Okay, we are giving some new topology on X star. Means we are defining some collection of subsets of X star to be the open set, new open set of X star under the new topology. Okay, we are defining some new sets to be the open sets in X star. Okay, so C may be compact in X, maybe C closed in X, but C not necessarily closed in X star. Okay, I mean we are declaring X star minus C to be open set in X star under this topology. We are declaring it like that. Understand? We are
Yes, sir.
defining that to be the open set. That's what only we are doing. Understand?
Yes, sir. Okay.
So, okay. So since we have started the compactification, so just tell me what you understand the compactification. Okay, I mean don't I mean if you can't remember those technical details, that is fine. But please tell me what. is actually the compactification? I mean, I know that there are some theorems, facts, etc. But what is actually the compactification? Any rough idea? But I mean, this topology Taugen system is not practically useful. I mean, this is the theoretical part. But what compactification? I mean, by compactification, what does you understand? Tell me. Rough idea is fine, but tell me what you understand through the one part compactification. Don't hesitate. Tell.
Sir, we add some point. If it is one point compactification, then
Yes.
we try to actually add a point to a space which is not compact, such that after adding that point, it will become compact.
Right. Correct. Very good. Yes, you have said correctly. So this is what actually the compactification is roughly. Okay. So you know that there are some. Okay. One second. So you must have seen that theorem that y is said to be one point compactification of x if um, y minus x is uh, singleton, right? And y compact Hausdorff. Have you seen this? Y is the one minute compactification if and only if y minus a singleton and y is compact plus Hausdorff. Have you seen this? Okay. Sudden network is disconnected. Okay, just hold on. Hi, am I audible?
Yes, sir.
Okay, sorry for the inconvenience because suddenly the internet connection. Just hold on. Okay, so the thing is that so you must have read this theorem that y is one multiplication of x if and only if y minus x and y is compact subspace and x is a subspace inside y. Have you seen this theorem? I mean, not exactly. You might not see the exact
Yes,
statement, but something similar. Yeah. Okay. So and also you have seen that any two spaces satisfying this property are homeomorphic, right? Have you seen this?
yes.
Okay. So, so can you tell me what is the one point multiplication of real life? I mean, what is R star?
Sir, S1. Sir,
Sorry.
unit circle.
Okay, unit circle. Why? Why? Give the rough idea. I mean, don't no need to say the
Sir,
extreme
because
technique.
R, if
Uh,
sir, if we will see it geometrically, then we bend R, we add a point R, then it get bended and make a unit circuit. And actually, R is a subspace of S1 as well as R is dense in S1 also.
right, correct. Yes, yes, fine. So, yes, very good. So can you, so in similar way, can you tell, uh, can you give an example of one space whose one point compactification is of this form? Figure 8. Sorry. So given space X such that its one point compactification is of like this. Can you construct one example? It's very easy. Think easily. Think in easy way.
Sir, will it be R square?
Sorry, very easy.
Sir, will it be R square?
No, 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 no. R square is one point compactification is S2, right? Because S2 minus a north pole is nothing but the R square, right? Correct.
Yes, sir, yes.
So
Sir, disjoint open interval.
joint open. Yeah, right, correct. Very good. So what she said actually, so disjoint open interval. Now if we add one, I mean, so disjoint open interval can be thought like as this. Now if you put one point in the middle and then add thing, then it will give this space figure it. Okay. So this is one example. Also one may think it as like this one interval, and in between one point we are putting the one circle. Sorry, I mean we are saying that it's one circle, and then if this portion and this portion is joined, then we will go the same figure. Understand? Understand? But don't be silent.
Yes, sir.
Okay, okay, so wow. Okay, so yeah, so any other person has any doubt regarding complexification or any topic you should ask.
Sir, can you please explain the geometrical meaning of implicit and explicit function theorem?
Yeah. By the way, if the implicit function in the notes, just asking. Can you please the implicit function theorem in note? Please tell.
Sorry,
Because
sir, your voice is not clear.
okay, one second. I'm okay. So I'm writing in the chat.
Yes, sir, it is there.
Okay, okay. Okay, so okay, so I mean, yeah, okay. So the implicit function theorem. One second. Okay, so consider the function f of xy is equal to x square plus y square minus 1. Okay, so it's is nothing but this this the whole circle, correct? I mean, this is nothing but the f inverse 0, right? Okay, now the implicit function, I mean, so observe one thing, that x square plus y square equal to 1 implies y equal to root over x square minus 1 for the upper half portion, right? Correct. So basically, I mean, in this example, we just in this circle, in a, I mean, 0 is a point in the image. So in the circle, we are getting some neighborhood of the circle where the second coordinate can be represented in terms of the first coordinate. Okay, y equal x square. I mean, so basically on that portion, it will be what? F of x comma root over x square minus 1, correct? So the second coordinate is represented by the first coordinate. So as a whole, we can think f as a, I mean, one second, how to say this? Okay, so let me define it actually. So basically, implicit function theorem ensures that under some function, any function, I mean continuous function, can be thought as a projection. For example, consider this example: f of x y is equal to x square minus 1. Okay, so on the upper half portion, the y, the coordinate, can be represented in the first coordinate. Okay. So on that portion, that any point x comma y is nothing but x comma root over x square minus 1. Okay, so so on this upper half portion, the function f is uniquely determined by its the first coordinate, right? Because y is root over x square minus 1, so only first coordinate we need to check. So on this first coordinate, we can think f as an projection map. The, I mean, so formally we need to say that we can get some map phi under certain conditions, such that f compose phi of xy is equal to x. This is the what is the most formal form of Spurious function theorem. But the main idea is that any continuous function under some conditions can be represented locally as a projection. That is, on some neighborhood u belongs to x, f of x1, x2, xn is equal to x1, x2 dot dot xk, where up to k is less than n. Okay, this is the main thing. So any context, so I mean, yeah. So this is the main thing. So geometrically this state, and for that consider the following example: x square plus y square minus 1. Okay. Also, yeah, one second. Okay. So consider another example. So consider f of xy is equal to y cube minus x square. Okay. So f of 1 is equal to 0. So by the way, the y cube equal to x square, its graph look like this. Sorry. Okay. F of 1 equal to 0. And by the way, do you know differentials of f? I mean, do you know this thing?
read it but cannot understand it properly.
Okay. Okay, so have you read the multivariate calculus? Because particularly this example involves that thing. That's why I'm asking. Have you read multivariate calculus?
Yes, sir.
So you read the multivariate calculus. So don't you know what does it mean by df11? I mean, okay. So notation might be changed. So you must know that how to calculate the derivative of f at certain point, right?
Yes, sir.
Okay. So tell me what is df11?
Okay, sir.
Okay. So tell me what is df11?
So -2 and 3.
Yes. Correct. Yeah. So I mean, yeah. So this is it. And now consider the map g of xy is equal to 3x plus 2y. Okay. Now consider the map psi is equal to f comma g. Okay. So then d psi at the point 1 1 will be of the form minus 2 comma 3 3 comma 2, which is invertible. So by inverse function theorem, there is a neighborhood w, the psi w to psi w is a diffeomorphism. Sorry, yeah, it's a diffeomorphism. Sorry, it's a diffeomorphism, right? Now take phi is equal to psi inverse from psi w to w. So now consider if now consider so so psi compose phi is equal to x comma. I mean psi is the inverse of phi, so psi compose phi x comma y is equal to x comma y, right? Now what is psi? Psi is equal to f phi x comma y g phi x comma y is equal to x comma y. So this implies f of psi x comma y is equal to the only x. So through this technique, finally we get the f compose some function is equal to the only first square projection of it. So this is what I'm trying to say, that under certain conditions, that conditions is the statement of the theorem, f can be thought as a function. Okay. So this is by what roughly the implicit function means. Do you understand? And have you did you tell anything about something like explicit function theorem?
No, sir, that was I mistaken.
Okay, so any other question or doubt you ask? Any other question or doubt you ask? Okay, so it seems you don't have any question. Okay, anyway, if you have any question, please ask me in the meanwhile. That's fine. So, okay, so today let's go with the separation axiom. By the way, did you read the separation axiom before? I mean, in the class, or it's totally new to everyone? Have you read the separation axiom? Have you read separation axiom?
Yes, sir.
Okay. So, okay, so can you give the definition of regularity? Anybody, please?
The space said to be regular if for any if for any closed set B, subset of X, and any point X which does not belongs to that closed set, we will get disjoint open subsets such that X belongs to one open set and the closed set is a subset of other open set. We can
Correct.
separate a point and a closed set by its disjoint open set.
Yes, right. Good. And what is the definition of normality?
So in
What is
case of normality, sir, we can separate two closed set by means of disjoint open set.
yes, that's very good. So, so give one example of a space. Okay, let me write it down. Give an example of a space which is Hausdorff but not regular. Give example of a space which is Hausdorff but not regular. Think about those spaces which you already know, then try to get the answer.
If we take our plants to elements, suppose A, B, and the tuple is defined as a subset of all this set AB.
What is
So
the
it is a
space?
house job, but it
Uh,
is not
what is the space X? What is the space
the
X?
set of set AB or 01.
It close it one. Okay. Close or open.
No, sir, it is a set of 01, set of two element. And topology is a power set is all the subset.
All the subset, right?
So if we take a point 0 and
Yes, also. I mean, it is obviously since all topology contains all sets, right? It is obviously normal and sorry, it is obviously regular, right?
yes,
But you need to find a map which is Hausdorff but not regular. Sorry, space which is Hausdorff. So you know the co-countable space, co-finite topology. You heard about this?
yes,
Okay, so can you think with that
yes,
co-finite or co-countable? Think about it. No, sorry, it's my mistake. Sorry, covariant topology is not Hausdorff, right? So so let me tell that. So thing is, R with K topology. You know the R with K topology, right? So you do you know that R with K topology? Mhm.
Yes, sir.
So the thing is, R with K topology is Hausdorff, but not okay. So try to understand that why this is Hausdorff but not regular. Please try. Take your time, think, and please let me know the answer or any or partial answer. Then also let me know. you get some satisfying answer? Did you get? Anybody got that at least why our technology is housed off at least? Anybody why RK is
Sir,
housed off? Yes, yes,
sir,
please.
RK topology is finer than the R with usual topology. That means RK has more number of open sets than R with usual topology. So that the open set, if we will take any 2 points in R with respect to usual topology and the open set that separates these 2 points, then that open set will also be there in RK. So we can separate the any 2 point.
Correct. Very good.
But I'm unable to get for regularity of RK.
Okay, can you please repeat? Can you please repeat? I don't get you actually. The last line what you have said.
Sir, uh, I am unable to understand why RK is not there.
Yeah, okay. So we need to check RK is not regular. Okay. So the first hint is the follows that show that the point 0 and the closed set K cannot be separated by open set in RK. So this is the hint. The point 0 and the set closed set capital K cannot be separated by disjoint open set, obviously. Cannot be separated by disjoint open sets in RK. This try to show this, right? Because if you can show this is not regular. So the point 0 and point K, I mean the set capital K, we will not get any closed subspaces. Sorry, we will not get any, we have any disjoint open subspaces. So yeah, so this is the hint. So now try.
Sir, the set capital K will be closed in RK.
Yes, yes, because in RK open AB minus capital K is a basis element, right? So open AB minus capital K is an open set in RK, right? So that's why capital K, which is the complement of the open set, is a closed set in RK. Understand? You understand that why capital K is closed?
Yes, yes.
Okay. So now try to show that the capital K and the point 0 cannot be separated by this joint concepts.
Then we can use Archimedean property
Yes.
with then around any, if we will take any neighborhood of 0, then that will contain at least one point of K.
Yes. Yes. That's yes. That definitely. But you need to come up with any open subspace of capital K, right? Yeah, right. Sorry. Yes, you are correct. Yes, no, no. The thing is, your argument is right that if I take an open source of the form open AB, then that open interval
0 is
contains.
the limit
Uh,
point of the set.
yes, no, no. The thing is, if you take the open AB, this neighborhood around 0, then what you have said is right. But one can choose the neighborhood open AB minus K around 0, right? Right. So for this situation, how you will argue? Do you understand my point? Do you understand my point? You have said correctly for open AB. I mean, for the open source type of open AB, you have said right. But in RQ, we have a base of the form open AB minus K, right? So if we take 0 and sorry for the interruption because the network is fluctuating. Am I audible to you?
Yes,
Okay, so yeah, so what you have said is correct for any open set of the form open AB at around 0. But one can choose an open set open AB minus K around 0, right? Then for this situation, what will be the argument? That's the point. Think of- I mean, you need to make a clever argument. I mean, you need to use some clever trick in order to use the Archimedes property again. That's the thing. Okay, think clever.
sir, your voice is cracky.
Oh, okay, sorry. Okay, let me write it down. Okay, let me write it. I'm typing on the chat. See the chat, the first chat. the thing is, yeah, if you take open neighborhood AB a minus k around zero, then how would it it? That's the problem, right? Think about it.
Sir, if we will take any open set containing K, sir, is it that neighborhood should contain the open interval 0, comma 1?
No, no, no. I mean, it's an open set containing k, right? It's an open set containing k, so it might not be a basis element, right? It might be union of some basis element, correct? So it
Yes,
is
sir.
not necessarily open interval 0 1, or it not necessarily may contain open interval 0 1, because we are in R, right? That's the point. The point is you need to modify the case when 0 belongs to open minus k in order to use the Archimedes property. Now flavored. I mean, it is very much it is. I mean, it is very closer to the previous algorithm. Just think a little slower. Any idea which rough idea you got? You got a rough idea? Okay, so the
Yes,
argument
sir.
poses. Okay, so let me take the argument now. So you will be an open set containing k. Okay, let's see. Okay, so one more thing is, one thing is that, so hold on. So since 0 belongs to open A minus k, so there is n such that 1 by n belongs to open A. Okay, Parsimony property. Now 1 by n belongs to k, which is subset of u, and u is open, right? So we will find a base element 1 by, which contains the point 1, which contains the point 1 by n, which lies inside u. Okay. So graphically, you would picture it into open 0, open AB. Okay. Some 1 by n is here, okay, and C, D are here. Right? This is the, almost the picture may look like this. So now choose Z such that Z less than 1 by n, Z greater than max T comma 1 by n plus 1. So for example, this is 1 by n plus 1. Now this Z belongs to open interval CD, and also this Z does not belongs to K, so this Z belongs to open interval AB minus K, right? So that U and V becomes, their intersection becomes null. So this is argument. Okay, so let me repeat it. So first choose, we have open AB. So we have open AB minus K. We're choosing an n such that 1 by n belongs to open AB. Okay. So 1 by n belongs to K, subset of U is open. So 1 by n belongs to CD, subset of U, but CD is open subset. Now consider following picture. Here is open A, open B, in between C and D, containing 1 by n. Okay. Now choose a Z such that Z is less than 1 by n, as Z is greater than a max of 3, 1 n plus 1. Okay. So this Z belongs to C, D, and since Z lies between 1 by n plus 1 and 1 by n, so Z is a point outside the set capital K. So Z belongs to CD as well as Z belongs to open A minus K. So the set U intersection B is not empty. So that's why R with K topology is not regular. Do you understand?
Yes, sir.
So can you please try that why RK R with sorry R with L? The lower limit topology you might know, right? Or you finish with R. Lower. Why the lower limit topology? No. Can you please try? Any idea? Okay, first try. Any idea how to approach this problem? Any idea? Okay. So, mm, so the argument goes as follows. So take A, B to close in RL with intersection F. Okay. Take A belongs to F. Now since B is closed, so RL minus B is open, right? and A belongs to B, that is A belongs to B complement. This implies we will get an XA such that third bracket A comma XA intersection B is equal to MB. Similarly, for each B in B, there is XB such that third bracket B comma XB intersection A is equal to MP. Now take U to be union of third bracket X comma XA, B to be union of third bracket B comma XB, A belongs to A, B belongs to B. Now claim is that U intersection B is empty set. That means the key. Now try to argue that why U intersection U were empty set. Please think about it.
Sir, I I am unable to understand the step where A belongs to A, then imply. Oh, okay, sir.
Yeah, okay. So now try to show that U and V order constructed. Their intersection is empty. Okay, so have you done that? Are you able to argue that why U intersection is empty? You can try it contrapositively. If the intersection is not empty, then what will happen? Okay, so I mean that's quite it's quite easy. Suppose if P belongs to U intersection V, this implies what? P belongs to some open AB comma X A intersection B comma X B. Okay. Now assume that A is less than B. Okay, so this is A, this is B. Now suppose this is X A. Okay, sorry. I mean, firstly, I mean this may be X A and this may be X B. But in this situation, okay, so this implies what? A less than P less than X A and B less than B less than P less than X A. So this implies P is greater than max of A comma B. Okay. So where P will lie, so if we consider the diagram more precisely, suppose this is A, this is the point B. Now since we have seen that P greater, uh, I mean, yeah, sorry, this is the point A, this is the point B. Now we have seen P greater than max AB, so suppose this point, this right hand side point is T, okay, and also T is less than minimum of XA, XB. So here somewhere either we might have XA and somewhere we might have XB. So in this situation, either B belongs to A comma XA or yeah. So yeah, that's the contradiction. Okay, you understand? I mean, so let me if T belongs to intersection B, this implies T belongs to third bracket A comma XA and comma B comma XB. Okay, this implies A less than T less than XA and B less than T less than XB. Correct. So these implies T greater than max third second bracket A comma B and T less than mean XA comma XB. So without loss of data, assume A is less than B. So these 2 point A, these 2 points B. Now T is greater than max AB, so T is on the right side of both A and B, and T is less than mean AB. So XA or XB are in the right side of T. So in any situation, B belongs to third bracket A comma open XA, which is a contradiction due to the construction we have done. So I mean this is a contradiction. So that's why U intersection B has to be empty. Yeah, this is the argument. So do you understand? Think about it. Okay. So yeah. So can you please try that metrizable space is normal? Sorry, metric space is normal. Can you please try to solve this? it is actually easy. Please try.
If we will take only two closed subsets in a metric space, then, sir, if R be the distance between these two closed sets,
Yes.
then, sir, we can construct a ball of radius R by 2. No, actually,
Yes, you are. Yes, right. Right. You are in the exactly the right direction. So basically, what I'm trying to do is that. So suppose we have a two closed set A and B. So for each point A in X, uh, we are getting an. I mean, we are getting an open ball B A comma epsilon A, which does not intersect B. And similarly for each B, we are getting B comma epsilon B. Intersection is empty, right? Now the claim is that, I mean, so we are getting some open balls here, okay. So now construct take mu to be union of A belongs to A, B A comma epsilon A by 2, B is equal to union B belongs to B, B of B comma epsilon B by 2. Okay. So now try to argue that U intersection B is empty. Okay, this is the argument. Do you understand what I'm trying to say?
yes, sir.
Now think about it.
we take a point X, which is
Yes.
on the ball, center at A,
Can you,
and
one,
it
one,
is also,
can you please be loud?
yes, sir, if we take a point X, which is in the ball, center at A, it is also in the ball, center at,
Yes.
so, because it is a metric, so the distance, we use the triangle inequality. The distance AB is less than or equals to the distance of a x plus distance of a b x.
Okay. Yes. Yes. Yes.
So it will be less than 1 by 2 epsilon a plus epsilon b. So it means that because a and b are disjoint,
Mhm. Yes. Correct. Well. Yes. Right. Fine. Good. So, just tell me one thing. Can you remember the tube lemma? No, no, sorry. Tube lemma is out of context. This question does not involve the next one. Show that every compact house dot space. Space means only space, not a matrix space. Just only topological space. Any compact house dot space is normal.
Sir,
Yes.
uh, if we will consider A and B are two closed set, then sir, since uh, and we will take since A and B are closed subset of compact space, so therefore they are also compact, being closed. So sir, we will take 2 points. A belongs to capital A and B belongs to capital B. And then since the space is Hausdorff, so we will get for these A and B open subsets UA and UB, which will be disjoint. Then we will consider all
Oh,
these
wait,
type of.
wait. Sorry. Can you please repeat the argument again?
Sorry, sir.
Can you please repeat the argument again?
Sir, we will take two closed sets, any two closed sets A and B.
Hmm.
Since the space is compact and the sets are closed, therefore A and B must be compact. And
Yes.
sir, we will take points A, small a from capital A and small b from capital B. Then since the space is T2, so we will get neighborhoods UA and UB around A and B, which will be disjoint.
Yes.
And
Correct.
then we will take all such neighborhoods,
Hmm.
all such open neighborhoods of A and B. We will collect them, take their union. Then both these collection will be an open cover for A and open cover for B. Then since A and B are compact, therefore we will get a sub cover of these two cover, which will cover A and B. That means that set will be open containing A and other will be open and contain B, and they will be disjoint also.
Correct. Very nice. Perfectly fine. Okay, so okay, one second. Okay, so have you heard about Ubishan's lemma?
Yes, sir, but I forgot.
That's okay. So the Ubishan lemma says that if x be normal and a be close in x, then there exists a continuous function f from x to close 0 1. So the f of a singular 0, f of b 0 singular 1. Okay, this is the Ubishan lemma. Okay, I mean this is the form you have seen, I guess, right? Correct. Have you seen this form or have you seen some different type of form? Have you seen this form?
Yes, sir.
Okay, so sorry, this is one thing. Okay, so using Grecian lemma, try to solve this so that uh, connected metric space having more than one point is so using Grecian lemma, try to show that any kind of metric space having more than one point is uncountable. Okay, so I mean, any idea what?
Sir, we have proved that every metric space is normal.
Sorry, can you please
So
repeat?
it is a, sir, we have done that every metric space is normal.
Okay, one second. Sorry for the confusion. Please wait for one. I shall be back soon. More than 5 minutes. So yeah, sorry for the late. Yeah, I was trying to fix the power issue. Okay, so please repeat the argument now.
Because it is a metric space, the metric space, so it is a normal. So for any additional closed subset, we have a continuous map from x to 0, 1, which map to A to singleton 0 and B to B singleton. So
Yes.
uh, the endpoint of interval 0, 1, we have a, so the endpoint 0, 1, we have a inverse pre-image and all the elements which are in 0, 1
Yes.
sir, after that I'm trying.
Yeah, you are almost correct. So take 2 points in the metric space. These are closed because the metric is a normal, house drop. So we will have a map from x to open 0, 1 where A goes to 0 and B goes to 1, right? Now X is connected, so image of F is connected, right? Correct. So basically image of F is a connected subspace of R. Now what is the connected subspace of R? The connected subspace of R are the real in itself or open interval, or the open intervals. Correct. Now anyway, the open intervals are uncountable. So image of F is uncountable. So these things are X uncountable. Right? Understand?
Sir, but the connected subspace may be the singleton. It is not giving
Sorry, the connected subspace.
so the connected subset, it may be the singleton set of R.
Yes, that's why the it is that the connected matrix is having more than one point, right? That's why initially it's taken is to be the more than point. So now you understand the whole argument.
Sir, can you please repeat the last statement of yours?
Because look, this is a map from x to g1. Okay. So image of f is the connect because x is connected and x is connected. F, right. So image of f is connected. Now what are the connected subspaces of R? Connected subspaces of R are the open intervals. Definitely the open intervals and the real line. This is the connected subspace of R. Sorry, the intervals and the real way. The intervals or the real line are countable. So image of f is an uncountable subspace. Is an uncountable set. So its domain should be uncountable, right? I mean, if x is countable, then image of f has countable, but image of f is uncountable, so x has to be uncountable. Understand? Do you understand?
Yes, sir.
So, okay. So, do you know about uh, Hill's extension theorem?
No, sir.
So, this was a oh, sorry, one second. Resurrection theorem is as follows. Suppose X be normal space, okay, and a subset of X be closed. Okay. Then any continuous map of A to R can be extended to all of X to R. So that it's a theorem that any country X normal is closed and any continuous map from A to R can be extended X to R. Okay, this is statement. So right now we are going to the proof. So using this, try to show the following. Uh, so let X be a matrix. Show that X is compact if and only if any continuous real valued function f from X to R is bounded. X is compact if and only if any continuous real valued function from X to R is bounded. Try to prove this using the regression theorem, and hint is use sequential criteria of compactness. This is the hint. Try to prove it. Any metric space such that X number if and only if any real world coordinate function from X to Y is bounded. Try to do it using sequential criteria. Total residence. Have you got any idea or partial? I mean, anything you got?
Sir, if x is then s and b function from x to r. Since x is a compact, so f of x is compact.
Yes.
Therefore, uh, x is bounded. Then, because x is compact, then every sequence in x convergent subsequence. So if we take a subsequence x of nk in x, which converges into x, by continuity property, f of x
Yes.
will converge to fx.
So one side you understand. So one side you solve. I understand. So the converse.
No, sir, I
Oh, you're trying.
will
You are
one
trying.
by
Right? Yes, yes. Try. You need to use the integration theorem for the convert, and also you need to use the sequential criteria of the compactness that
Is it that a compact metric space should be bounded or
yeah, common matrix means bounded and sorry, totally bounded or complete. But also compactness, there is one characterization that any sequence has a convergence subsequence. Okay, you need to use that for the converse part for this problem actually. Okay, so the converter goes as follows. So uh, yeah. So let x not compact. Okay, so this implies there exists a sequence xn having no convergent subsequence. Okay, So we will. So there will not. I mean. So there is what is subsequence? Okay. So I mean, yeah. So I mean, since this sequence set xn has a convergent subsequence, this implies the sequence set xn has no limit point, right? This implies the sequence xn is a closed set, is a closed subset of Rn. Okay. Now, define f. This is the set a to R by xn goes to n. So it is obviously continuous. Okay. And now, by T's extension theorem, there exists an extension f tilde from x to R such that f tilde restricted to a is equal to f. But observe that the by the construction of f, f is unbounded, right? Because it takes any big natural number. So this implies what? This implies f tilde also unbounded, right? So this tells what? We get a map f tilde continuous from x to R, which is unbounded. But I mean, this is a contradiction of the given hypothesis that any real valued function x to R is bounded. So that's why the space X is compact. This is the argument. Do you understand?
Yes, sir.
So
Sir, the function,
yes,
sir, the function f defined from A to R, so it map to be the sequence xn to those points where it is not convergent.
no, no, no. The thing is, the I mean, contrary, we have assumed that X is not compact. Okay. Now the sequential compactness says that X is compact and only a sequence has a convergence of sequence, right? But since we have assumed that X is not compact, so we must have a sequence X which does not have a convergent subsequence, right? So, I mean, it does not have a convergent subsequence because xn has no limit point. So that's why the sequence xn is a closed set. And then we are using the extension theorem by defining the map F from the closed subset, which is the sequence set xn to R, by defining xn goes to n. Okay, so that's what we are doing.
So,
Understand?
sir, how to prove that it is unbounded?
Oh, unbounded means what? Pinball. I mean, unbounded image of f is unbounded. Image of f is bounded means what? Image of f is lies inside an open ball, right? But the thing is, xn goes to n. So if you take any open ball, you will always get a natural number. I mean, if you get any open interval, you will always get a natural number big enough, which is outside that open interval, right?
Okay, sir, yes, sir.
So yeah, that's one. So you have gone through the three sections and options, right? So can you uh, please check that? I mean, so observe one thing that uh, teach the extension theorem implies Wilson's lemma. Can you please check that the teach the extension theorem implies the Wilson's lemma? I mean, it is very much obvious, but to know that whether you have observed. So if you observe this, that please give the argument that teach the extension theorem implies the Wilson's lemma.
Sir, here, sir, in the Purishan's lemma, if we will
Huh? Then then
sir, I got confused.
the T-selection theorem that I mean, so okay, so let me. So basically, the Wilson so T-selection. So suppose A, B are two disjoint closed spaces are closed. Okay, in it. So this is so these are assumption. Okay, we are assuming the AB to closed subsets and disjoint. Okay. Now, what we are doing, we are taking this map A union B to 0 1. Sorry, A union B to R by the sending the set capital A to 1 and sending the set capital B to 0, right? So by T-selection extension theorem, if we call this map A, by T-selection extension we will get a map A from X to whole R such that A goes to the set A goes to 1 and B goes to 0, right? I mean, because the F tilde extension, that is F tilde restricted to A union B is equal to F, right? And by construction A goes to 1, B goes to 0. So that's why this holds. You understand?
Sir, can you please repeat?
Yes, yes. So for the Wilson's lemma, first we need to come up with some. We need to have some closed disjoint open closed space of X, right? So here we have taken two disjoint X, right? Now we are taking a map small A union B to R by defining A goes to 1, B goes to 0. Okay. Now A so by testing map. Now by Trinity extension theorem, we can extend this map F tilde to whole of X such that F tilde restriction to A union B is equal to small f. So this is what F tilde sends capital A set point 1 and the sends capital B set to the point 0. Okay, this was the Wilson's lemma. Wilson's lemma means what? We need to find a function small f from X to R such that one set goes to point 1, another set goes to point 0. And this is what it is we got, right?
Yes, sir, understood.
Yeah, yeah. Okay, so today is 9. So, so let's start. And if you have any doubt or any question, you can ask me, or also you can answer next question. Okay, but please do one thing. In the chat box, I have shared a Google form link. Please mark your attendance by submitting the Google form. Okay, please give your attendance. Did you give your attendance? You gave your attendance?
Yes, sir.
Oh, thank you.
Yes, sir.
Yes,
Yeah.
sir.
Okay, so yeah, so let's stop here. So if you have any doubt, you can ask me.
Thank you, sir.
Yeah. Okay. So I am disconnected.